Julian Barbour is a renowned physicist, a visiting professor at Oxford University, who has got a particular interest in the nature of time and in the origins of the universe. His new book, The Janus Point, represents 5 decades of work. And Martin Rees says of the book that Julian Barbour is a profound and original thinker with a boldness to tackle some of nature's deepest problems. He's also a fine writer, and he renders his book, despite its conceptual depth, accessible to anyone who has pondered the mysteries of space and time. So, Professor Barbour, welcome, and thank you very much for coming to talk to us today. I understand, Professor, that you haven't followed the normal academic road or route to academia, but you've been an independent physicist. Could you tell us why you took that particular route, and has it been easier or harder?
I took the route because I wanted to study really basic questions, basically what is time, what is motion. I got very interested in these issues when I was starting work on a PhD in astrophysics in Munich in Germany. And quite by chance, I read an article in the local newspaper about an article that Dirac had in 1963 in the Scientific American, in which he had fundamentally questioned the notion of space-time and saying he didn't think that four-dimensional symmetry was a fundamental feature of the physical world. So this was pretty radical, and it made me start thinking, well, what is time? A question I'd never really asked myself before. And much about the same time, I came across Ernst Mach's writings, where he also, he said the same as I had come to the conclusion that change is the primary thing, that we could never talk about time if things didn't change. So I got very interested in that. I eventually did a PhD on a fairly standard thing in general relativity at the University of Cologne, and then was thinking to get a position at a university in Britain and become an academic. But meanwhile, I had been earning money on the side, translating Russian scientific journals. I'd learned Russian as a hobby while in Munich, and realized I could earn money quite well. And I spoke, when I was back in Britain, I talked to Felix Pirani, who was a leading relativist, who was an academic at King's College in London, and said, could he advise me what it's like being in academia? And he said, well, if you can do 3 things, yes. If you can handle the administration, give the lectures, and produce 1 or 2 good research papers a year, yes. If you have doubts about any of those 3, no. And I felt I could manage the administration and the lectures, but not 1 or 2 good research papers on what were clearly among the most fundamental problems in physics. And so I decided to go independent. And for 28 years, I earned my living by translating Russian scientific journals. I dictated them. I was keeping 2 excellent ladies. They were marvelous, busy typing away my things, and they went off to a publisher in New York, Plenum Publishing, and also to the American Institute of Physics. And that left me about 1/3 to 1/4 of my time to do exactly what I wanted, with no publish or perish pressure, which was already an expression back in the early 70s. And for me, that worked out perfectly. I was essentially earning the same amount as a professor at a British university, and I was having about the same amount of time to do research, possibly even a bit more. And eventually got my first paper published, and it came out in Nature in 1974. Wow. On Mach's principle. And that then led to an interaction with Bruno Bertotti in Italy, and I've really never looked back since then.
Right. So you didn't really find it any disadvantage then, not being associated with a university. You could still make an impact.
Well, yes, I was very lucky in that interaction with Bertotti, because eventually our second paper, which was published in 1982 in the Proceedings of the Royal Society, I think this really is now it definitely shows that Mach's ideas were right, that you can, Mach conjectured, in putting it in modern terms, that the inertial frames of reference that must be used to formulate Newton's laws in the standard form, you can understand that they are determined by all of the masses in the universe. And a key thing, now one way of doing that would already been discovered before general relativity was discovered. And in fact, Schrödinger in 1925 wrote a beautiful paper on it. But that way of implementing Mach's ideas led to an effective anisotropic inertial mass. And Bertotti was very acutely aware of that. And this was the idea that I'd independently discovered, and at the same time getting rid of time as something, as in Newtonian physics, which nobody else had done. But then Bertotti and I came up with a method which I now call best matching. And in that, there is no anisotropic inertial mass. So you recover, it's a very strong test that there's no inertia, no anisotropy of inertial mass. So that was
I'm going to ask you about best matching in a moment. But sorry, you were going to say something?
No, so I would say just that paper of ours in 1982, I think that is increasingly recognized as being the way to implement Mach's principle, and it's a vindication of Mach, and it exactly the same sort of procedure that underlies it is in general relativity as well. It underlies the structure of general relativity when you look at it as a dynamical theory.
So having lived with Mach for so long and considered the principle and his work, do you still believe that the principle is true and valid, or rather like Einstein, after a certain time, who took it up very, very quickly and with his general theory, came to abandon it later on and considered that it wasn't a theory which could be sustained? Have you maintained your view of Mach?
Yes, and if I may say so, I think it's because I went about it the right way and Einstein didn't. Now, that sounds dreadfully arrogant, but the fact of the matter is, I mean, if Einstein was here, I'm sure he would agree with me that he set about implementing Mach's ideas in an indirect way. And it came about because of his brilliant success with special relativity. And after special relativity, 2 years later, he had the idea of the equivalence principle, where he went from inertial frames of reference moving uniformly with respect to each other to frames of reference that can be falling in a gravitational field or with a uniform acceleration. So he showed that uniform acceleration showed up in the same way as a gravitational field. And that, together with the example of Maxwell's work in creating the theory of electromagnetism described through local differential equations, expressed through differential equations, was much more important for arriving at the structure of general relativity. And so he never really attacked Mach's principle in the right way, because, I mean, when I was starting interested in this back in 63, 64, I read Einstein's papers from while he was creating general relativity. And I said to myself, he's not setting about this in the right way. We must go back to Machian first principles. And that has worked out. And then what is really wonderful is to find that when you unpack general relativity and see how it really works as a dynamical theory, then you find that it actually is very Machian. Now, the key thing is that for that to be true, you need a spatially closed universe. So this is what was always attractive to Einstein. So if the universe closes up on itself, then I would say it is perfectly Machian.
Right. Okay. Let's move on to the book.
Yeah.
It's called The Janus Point. And could you just tell us what is the Janus Point? And can you also maybe link it with what we might be more familiar with, which might be the Big Bang?
Right. Well, this is where statistical mechanics and entropy come into the story. So I've always been interested in the problem of the arrow of time. Where does the arrow of time come from? And this really reached crisis point in the 1890s in a famous debate between Ludwig Boltzmann and Ernst Zermelo. And the dilemma, the problem is that the Newtonian laws of motion, or all of the ones, pretty well everything that's known that certainly can affect the issue, they are time symmetric invariant. They work exactly the same way in which you assume that time goes. But everything we see around us all has a direction. We all get older in the same direction. Entropy increases in a closed system. Electromagnetic waves are observed to be retarded, and there's lots more. So what's the origin of that? And that's really been a mystery back since the discovery of the laws of thermodynamics in the 1850s. Kelvin wrote a very significant paper in 1852 with the title "On a Universal Tendency in Nature to the Dissipation of Mechanical Energy," which was very influential and still is influential. So I've been very interested in this, but also in connection with my Machian ideas, I had by chance come across a very famous paper by Lagrange in 1772, where he had worked on the Newtonian three-body problem, the famous problem that gave Newton headaches of the Earth, Sun, and the Moon moving in their mutual gravitational fields. And the result that Lagrange got, which was very interesting, that if you measure the size of the system, the three-body system by, well, it's half the trace of the moment of inertia tensor, or you can also call it the center of mass moment of inertia, which is basically the size of the system, sort of the diameter. If the energy is non-negative, so it's either zero or positive, then that, excuse me, that quantity in all solutions in the distant past is infinitely large. It comes down to a minimum value, and then it grows up again to an infinite value again. So it's governed by Newton's equations, which are time reversal symmetric, but the solution divides into two halves. And then what I also knew is that at that minimal size, around that point of minimal size, the distribution of the particles is more uniform than anywhere else in the trajectory. So as you go away from that central point in both directions, the distribution gets more clustered. And that defines an arrow of time on either side, pointing in opposite directions. So this gave me the idea of what I call the Janus Point of the Roman god who looks in two opposite directions at once, because there are bidirectional arrows from that central point there. And I suddenly thought, well, this was in discussion with my two collaborators, Tim Kozlowski and Flavio Mercati. I said, ah, we've got the solution to the problem of the arrow of time.
Because it faces both ways at once, you mean?
It poses both ways at once. So if we imagine beings that we're on one side of that Janus point, what do we see around us? First of all, we see the local behavior of particles like the solar system behaving in accordance with Newton's law, which is time reversal symmetric. But in the large, we see an arrow of time. The universe is getting more clustered, more clumpy. This is exactly what cosmologists are telling us. That's what the universe, that's what the history of the universe is like. But if we look towards the Janus point, because it's all very uniform and sort of a bit like a fog, we wouldn't realize that there's another half universe on the other side.
And what if you were on the other half of the universe? Would you see time still flowing in the what you consider the usual direction, or would you?
Yes, it would seem to be exactly the same on that side. And again, people on that side would be unaware of our existence and that it could be going on this side here.
And is there any way to distinguish which side you might be on? Probably.
No, because they would be qualitative. They wouldn't be identical. They wouldn't be mirror images of each other, but they would be qualitatively the same.
So not a multi-universe, but a bi-universe.
A bi-universe, yes. Yeah, that was the idea. And we sent off a paper to Physical Review Letters, and they were clearly worried because we were claiming we'd solved, got the solution to a big thing. They actually sent it to 5 referees, of which, and eventually it was accepted and got quite a lot of attention. Yes, they gave it a star or whatever they called it, a editor's recommendation, and they got somebody to write an article about it. So that was very gratifying. Okay,
so how does it compare with the idea of the Big Bang? What are the differences between the idea of a Janus point and its expansion, which seems very similar on the surface to a Big Bang, which also expands out, but that's only going in one direction, time-wise?
Well, for quite a while we thought, I must say let me say that I've been working on this ever since the idea occurred to me in 2012. So that's now 9 years. And ideas have been developing all the time. And initially, we didn't probably pay enough attention to the fact that the Janus point, or Janus point as I call it, but you can take your pick, is the size of the system does not go to 0. There's not a total collapse or a total collision, as the specialists call it, in this, when you get this U-shaped curve for the size of the universe. Whereas we think in the Big Bang that the size goes exactly to 0, at least it does in quite a lot of the solutions. And it's only bit by bit that I and my collaborators came more and more to grips with this issue of what happens if we take the situation when it goes to 0. I don't know whether we want to postpone that till later in the discussion or whether I say something about it now, because that's now what I'm getting actually much more interested in. Is the situation where it is actually 0. And in that case, there aren't 2 halves. One of those halves goes missing and there's only 1 half. But what happens in that 1 half is still is extraordinarily interesting, I would say. Okay,
we'll leave that towards the end of the talk, because it sounds to me that that's just outside the scope of the book. Am I right?
It is brief. The really radical idea that came to right at the end of writing the book is mentioned towards the end of the book, but only in a page and a half, which was free after the text had been set, and I could squeeze in some more text. So shall we come to that when we've gone through some of the ideas? Because virtually everything that is in the book as it stands, I would say, still stands in terms of the key ideas.
Okay. And let's move on then to the question of entropy and how that's naturally associated with a increasing disordered system, and why you feel it's necessary that we need to replace that with a different concept.
The realization that came to me was that thermodynamics was discovered through this marvelous little book that was published by the Frenchman Sadi Carnot in 1824 with the title On the Motive Power of Heat, of fire, motive power of fire. And I don't know if you're familiar with it, but it's an absolute masterpiece. In about 6 pages, he establishes what is the maximum, how would you make a steam engine maximally efficient? And in the process, he lays all the foundations of thermodynamics, except for one condition, which was added 26 years later by Rudolf Clausius and also by William Thomson, later Lord Kelvin. And Clausius's one addition was that heat does not flow spontaneously from a cold to a hot body. But all the other ideas of reversible transformations, the fact that a steam engine can't work with 100% efficiency, that some heat has to flow from a hot body and be dumped in a cold body and is lost and is wasted. All of that is in Carnot's little book. And Einstein said the one branch of physics that he thought would never be overthrown within its proper domain of applicability is thermodynamics. Mm. And then it occurred to me that all of the work that has been done on entropy, amazingly to this day, essentially works conceptually as if you've got a system in a box, because that's the key thing with the steam engine. The steam has got to stay in the cylinder as it's going backwards and forwards, or the train will soon come to an end, can't keep going. And thermodynamics was discovered 80 years before the expansion of the universe was discovered. So I said to myself, are all of the wonderful theorems and results that have been obtained in phenomenological thermodynamics, where you're just measuring pressure and temperature and things like that, or when you're trying to explain it with the atomic hypothesis using the techniques of statistical mechanics, which were all developed so wonderfully in the 19th century, first really by Clausius, then by Maxwell, then Boltzmann, and finally by Willard Gibbs. Can you just apply them in an expanding universe? No. Is the expand, particularly now that the universe looks as if it's even accelerating its expansion, is it appropriate to use the same concepts to describe the universe? And I come more and more to the conclusion, no, it isn't. I think it can't be right. You must think about it in a different way. As Kepler said in a different context, we must philosophize about these things differently.
So is there a better concept that you can use instead?
Well, yes. And in fact, so I'll just stick with Newtonian particles interacting through Newtonian gravity for a start. Most people would say the relevant quantity there is the Newtonian gravitational potential. You have any two particles contributed. So if you have a total of n particles, any two of them, you multiply their masses together and you divide by the distance between them. And then you add up all those contributions, and that's the Newtonian potential energy. And I think if you ask nearly all scientists, they would say that's what governs Newtonian Newtonian gravity, the n-body problem, as it's called. Yeah. However, if you're actually saying to yourself, my n-body system is the whole universe, there's a much more fundamental quantity, which people who work on the n-body problem, they have two names for it. One is either the normalized Newton potential, or it's also called the shape potential. And that is essentially a scale invariant form of the Newton potential. Now, the Newton potential, when you write it down, it doesn't matter how you change the coordinate system, whether you rotate the coordinate system or displace it. So that's equivalent actively to moving all the particles or rotating them into a different position, that leaves the value of the Newtonian potential, the Newton potential, unchanged. But if you increase all the sizes or decreases, that changes it. It's not an invariant of what's called the similarity group. But this alternative quantity, which is appropriate for describing how a universe of n particles behaves, is this quantity that's made scale invariant. You multiply it by the same quantity that I mentioned earlier, the center of mass moment of inertia, or rather its square root. And then you get something which is scale invariant. It's a pure number. And there's absolutely no shadow of doubt that that is the fundamental thing which is governing Newtonian interactions, gravitational interactions, if you're considering a universe of a certain number of these particles.
And what does it measure then? What is it a measuring of?
Well, I would say that you could have arrived at it very easily. A mathematician could easily have arrived at it if he'd never heard of Newtonian gravity. If you'd said, give me a number of point particles with certain masses, and then find me a quantity which tells me to what extent they are clustered or uniformly distributed. Now, there's many different quantities that you could come up with, but there's just one which stands out because of mathematical simplicity. It's the ratio of two lengths. So to get something which does not depend on scale, you have to take a ratio of two lengths. So one of them is called the root mean square length, and the other one is called the mean harmonic length. Now, these are mathematically distinguished quantities. So they're mass weighted, so they're democratically mass weighted. The bigger masses taken are more important. The mean harmonic length is dominated, the main contributions to that come from the large distances. The mean harmonic length, the main contributions come from the short distances, because the mean harmonic length is the inverse of the Newton potential. So when two particles get close to each other, the Newton potential gets bigger. And so that's a quantity which stands out a mile from anything else as the one to choose. And lo and behold, it is that pure number which governs Newtonian gravity. So this is clearly a very fundamental quantity. Now, the interesting thing about that is that as the universe expands away from this Janus point in either direction, that quantity just gets bigger and bigger, reflecting the fact that the universe is getting more structured. It's not getting more disordered. It starts off in its most uniform, down at the Janus point, that's where it's most uniform, and then it gets more structured. And moreover, that structure is very impressive, because whenever a Kepler pair forms, when two particles get gravitationally bound and start rotating like a Kepler pair, that Kepler pair becomes a rod, a clock, and a compass all in one. So as that system expands out, you could find that a great number of these Kepler pairs form, and all their major axes keep a fixed angle, or the angle gets ever better fixed relative to each other. They all, as a clock, they all march in step. They may be going at different rates, but the ratio of the rates gets ever more perfectly constant. And they're all pointing, and they also define a length, a ruler. So you find that all of these things, so a Kepler pair is a rod, a clock, and a compass all in one. And out of that pretty chaotic situation at the Janus point, where the whole universe is pretty uniform and the particles are moving around like a swarm of bees, as it expands out, suddenly this beautiful structure is formed. It's incredible.
So this is
if I can just come in, that is just the exact opposite of chaos increasing and disorder increasing.
That was exactly what I was going to say. It is the exact opposite. So how is it that for 100 years or more now, people have looked at increasing disorder as a mark of the progress of time and taken that as what's happening in the universe. And yet your view is pretty well the direct opposite of that, that it's increasing complexity.
Yes. Well, I think it's a historical reason. I think it all comes back to the way thermodynamics was discovered and the way Boltzmann thought about this. If you have a closed system, if you have molecules trapped in a box, and by some means they all start off in the bottom corner, one corner of the box, they will spread out and fill the box uniformly. And that's what people call increase of disorder. That's fair enough. But that uniform distribution is because they bounce elastically off the wall of the box. If you read any of the papers by Maxwell Boltzmann, they start off by saying, we assume a box with atoms or molecules, and the atoms and molecules bounce elastically off each other and off the walls of the box. Now, if the walls of the box weren't there, what happens? And this was out in space. Actually, what happens is all those molecules go off out into space, and you find that they become, that they're evolving in accordance with Hubble's law for an expanding universe. It's completely different from the standard story.
It is.
If they can interact gravitationally with each other, they will do what I was describing. They will become Kepler pairs and things like that.
Is there any connection with this increasing complexity, which you can see around us? We only have to look out the window and see, growing life. Is there any connection though with that and Schrodinger's insight? Of course, he wrote that famous book on what is life.
What is life?
And he almost defined life as that which, I think if I'm quoting correctly, that which feeds off negative entropy, as if like life stands out quite differently from the rest of the universe.
That's quite right. He got it wrong at the first attempt, and he was corrected by a scientist, and he rather embarrassingly put a footnote, I think, in the later editions.
Oh, right.
But I tell you what I think now. I've come to the conclusion that entropy is overused as a concept. I think its proper use is very restricted, and it should only be used when you have a system in a box that's confined. And I much prefer Kelvin's description, which is where he talks about a universal tendency to the dissipation of mechanical energy. And that's what Kelvin called the second law of thermodynamics. If you look at his later pronouncements, he calls that paper of his the second law of thermodynamics. It's one of the many formulations of the second law. Now, if you look at what makes it possible for vegetation to grow on the earth and so forth, it's the high energy photons that come from the sun. They bring about, through photosynthesis, they help plants to grow. And then at night, the earth radiates low energy photons. So basically for every high energy photon that comes in from the sun, about 20 go off from the earth. And that is a classic, so you could describe that as dissipation of mechanical energy. So Kelvin is spot on. He'll never be, I mean, I say in my book, he can sleep in peace in next to Isaac Newton in Westminster Abbey.
Yeah.
That's never going to be overthrown, that idea. But I think it's very unfortunate that he used the word dissipation. He said it can't be destruction of energy because only, essentially saying only God could create or destroy energy. But he said, he used the word dissipation, but I would say a much better word is spreading. All the time I was writing that book, I was struggling with this word dissipation. And towards the end of the book, I started introducing the word spreading. And right at the end of the book, something came to me, which was this analogy. Take a a blob of ink on some paper and you push your thumb down on it, you'll just get a smudge of that ink underneath your thumb, because the thumb is effectively being the box which keeps the molecules in the box and makes them spread out in the box.
Yeah.
But if instead you were an artist and you took a fine pen, and with that fine pen, you took the ink and you drew a beautiful picture, you would spread that ink, but you could create something very beautiful or something very detailed. And only about 2 weeks after I had put that into my book, I went down to the brook near where I live after it had rained, and there's a tree hangs over the brook where it flows over a ford. It's a very beautiful spot. A lot of people go down there and watch it. And I noticed the water drops falling off the tree. Now, those water drops, as they fall, all the mechanical energy is in the falling drop. It's all concentrated in the drop. It hits the water and it spreads out with these beautiful concentric circles. That's spreading of mechanical energy. But now, is that disorder? If you watch any talk on the second law of thermodynamics, they'll nearly always talk about cups falling off tables and breaking and that they never go back again. They don't mention the spreading out of those concentric waves. And in fact, that is actually retarded radiation. So in fact, it shows that Kelvin's original talk of dissipation of mechanical energy actually covers retarded radiation as well.
Quite foresight.
So I think it's definitely clear that using the word entropy if the system is not confined is just inappropriate. And in fact, there are no systems that are confined in the whole universe. Nothing remains like that. Stars for a long time are in quasi-equilibrium, but they're not in perfect equilibrium. And in fact, they are spreading things out. In my book at the end, I say that there are two main processes that are happening in the universe. There's clumping, and there's what I call spangling, which is spreading out energy in all directions. I mean, obviously this was looking to the American edition of the book for the Star-Spangled Banner. But it's an appropriate word, I think. And I think if you look around the universe, you can say that's basically what's happening.
So you have, I believe, replaced the idea of entropy with a new word. You've coined a new word to describe it then.
Yes, we introduced in my collaborators and I introduced a word which we called entaxy, which you can define, and that actually decreases that. So in thermodynamics, you have this important concept of a macro state and a micro state. So a macro state is typically, the most fundamental one is the energy of a system, an enclosed system, and then its volume. So basically, your system will be described by its energy and the volume that's enclosed. And then Boltzmann's great idea was to say, what about all the individual microstates, what the system as a whole is doing, what its trajectory is in its phase space. And he interpreted entropy in those terms. And I think this is perfect as long as you can talk about a confined system. But if you're talking about the whole universe and it expanding, I think that's just inappropriate.
One of the important concepts that you have in the book is the idea of shape space. Could you tell us how that's important and what that is?
The importance comes from the realization that objectively astronomers do not see the universe expanding, they see it changing its shape. That's the real evidence. I mean, we start off with the fact that Hubble discovered the expansion of the universe through the observation of redshifts, and redshifts are ratios. And the best way to think about the expansion of the universe is that the typical diameter of a galaxy divided by the typical separation between two galaxies is decreasing as time goes on. That's an objective fact. There's no real shadow of doubt about that. But if you're to say that the universe as a whole is expanding, you would really need a ruler outside the universe to compare it with.
Yep. And
so I would say that that's just the wrong way to think about it. You should say that the universe is changing its shape. And in fact, if I may say, I was on the wonderful In Our Time program 19 years ago with Melvin Bragg and Martin Rees, where I stuck my neck out and said, the expanding universe stinks. It's changing its shape. Martin said, oh, Julian, your philosophy may be quite good, but I think you're forgetting 95% of the physics. But I think actually we've got the physics now in place as well, because the idea was to describe the universe in terms of its shape. So there's a very beautiful way of doing this if you imagine a toy universe of just three particles interacting in Newtonian gravity, because if you have three particles, they form a triangle. There's three sides of the triangle, but only two internal angles are what determine the shape. So basically, a universe of three particles is described by just two pure numbers, two angles. And that means that you can represent that, each possible triangle, by a point on the surface of a sphere. I've got it. Was one, I don't know where I put my sphere. But so basically, each point is a shape of the triangle, and the triangles that have the same longitude but opposite latitude are mirror images of each other. And if you imagine the shape of the triangle changing continuously, you will get a curve on that sphere, on that shaped sphere. And it's amazing how much you can do with that shaped sphere. Now, in that complexity quantity that I spoke about, that can be defined for the three-body system as well as any number of particles that can be defined. And so you could use the complexity to, like the energy, as a state function. Just as the energy serves as the state function in statistical mechanics, we take the complexity as the state function. And when you do that, you find that the amount of the shaped sphere in the three-body problem, but it's much better to imagine a multidimensional shaped space with many particles, you find that the region of where the complexity is high is only a very small part of the shape sphere. So most of the shape sphere has very uniform distributions, and it's only, so to speak, on the edges of it that you find that the complexity is high. So if you can measure, you can have something like an entropy quantity, which is the volume of shape space that corresponds to a given complexity, and that quantity will decrease as the evolution goes on. So and that's reflecting the fact that the universe is getting more structured. So the universe as a whole is getting more structured, and the quantity that you would define exactly as Boltzmann did. Boltzmann said, for a given value of the state function, for a given macro state, how many microstates are there? And the microstate in our situation is defined by the volume of shape space that is occupied for a given complexity. And that goes down. So that reflects the fact that the universe is getting more structured. So that works very nicely. So what we're saying is that a system which is confined, as in standard thermodynamics and statistical mechanics, behaves in exactly the opposite way to one that is not, and can evolve freely, has no bounds, so to speak.
Okay. Tell me, is it from shape space that time itself is being constructed, shall we say, through an ordering process? And is this where your best matching idea comes in? Have I got that right?
Well, not quite. I should have got my triangles to illustrate this, but I can do it with my hands.
All right.
Let me say, first of all, if just take an ordinary Newtonian system,
Right.
and let's take the three-body system, the ordinary Newtonian system. We generate a solution in the standard way, and then we throw away all the information except the successive shapes. That then gives us a curve in shape space. And all the no information has got lost. All the information that was in the original solution is all there if you know how to interpret it.
But don't you have to input the order of the shapes as they change, so that you
Well, yes. I mean, but you see that. I mean, once you take your Newtonian solution, which actually has a lot of redundant information in it, relating to where the coordinate origin is relative to the particles, the orientation of the axis, and things like that. Once you just take the successive shapes, you just get a curve in shape space. And on the shape sphere, you just get a curve on the shape sphere. And all the essential information is in that curve.
When you say successive shapes, do you mean similar shapes?
No, they're different shapes.
But aren't they similar in the sense that they closely? Isn't that where the ordering idea comes from? If I'm trying to understand the idea of where you get order from this kind of structure. If you simply have a set of shapes and you throw them on the floor, you can pick out an order from them by saying, well, this one looks like it should. You could put it in an order in terms of similarity of shape.
Yes, that's right. Yes, it was. I think the only thing was your use of the words similarity. It's changed slightly, would be perhaps a better way to put it. Would you agree with that?
Oh yes, yeah,
that's what it is. No, you're quite right. So I mean, I'm always saying that you could throw down all the shapes in a heap, and my 6-year-old grandson could pick them up and put them in the right order, except that you wouldn't be able to say definitely this is the order or that's the order in the Newtonian terms, but you would be able to say in which direction it's getting more clustered.
But don't you need an intelligence of some kind in order to perceive that best matching? It doesn't arise naturally. Your 6-year-old grandson could do it, but only because he's intelligent enough to do that.
Yes, well, that's what the people who've discovered the laws of nature, things like that, we're all humans. I mean, I think we can only say that we're part of the universe, and somehow or other we've learned how it works.
No, sorry. What I'm trying to get at, if I can try and make my question clearer, is this best matching approach. Is that not something which is done entirely inside one's head? It doesn't exist out in the universe as such, and that the order is therefore imposed by our perception of similarity. Or have I misunderstood that?
I think a little bit. So first of all, there's two separate issues here. So actually, we haven't yet got to best matching at all in the thing. We've just, I mean, you're quite right. I mean, to put it in another way, if a picture had been taken of me every month of my life, or every 6 months of my life, and the photographs were just put in a heap. Somebody could come along and put them in order, and knowing that people get older in the world, that you would be able to say, this was when I was younger, and this is as I got older. So that's chronology. That's putting the order in like that. But a different matter is what I call best matching. So I haven't got my triangles with me, but let me illustrate it by my.
Yeah.
What a pity I didn't bring. I tell you what, why don't you stop the recording for a minute? I'll go and get my triangles.
I'll put it on pause. Okay.
Yeah, put it on pause. Right, let's. So Newton imagined. So this is to explain the idea of best matching. So Newton imagined that there's an absolute space. So that's like the kitchen where I am now. And in that space, you know exactly, if you could see it, you know exactly where every particle is. It has its definite position. And Newton said, every particle, if it's not affected by some force, will move in a straight line at a uniform speed. And Mach objected to this. He had two sayings. He said the universe is given once only, with its relative motions alone determinable. Only relative motions, the only things that you can hope to see are how the separations between particles change. Also, he said, it's utterly impossible to measure the changes of things by time. Quite the contrary, time is an abstraction at which we arrive from the changes of things. So, and Mach called for a reformulation of dynamics that respects those two statements. And that's basically what my life's work was at the start, at least anyway. And a lot of my life's work's been involved in that with my collaborators, in the first place, Bertotti, and then some other very good collaborators. So to get around that, you have to assume that in some senses, the universe is a single system, a closed dynamical system. And you can either do that with imagining particles in Euclidean space, or you can do that with dynamical geometry, which leads to Einstein's theory of general relativity. But if you had just three particles, and in one instant, they form the shape of this triangle.
Yep.
And in another instant, they form the shape of this triangle, which is slightly different. If I try and put the two triangles on top of each other, I can't bring them to exact overlap. I move them around. I swap the mirror image, and I can't bring them to exact overlap. But what I can do, if there's a finite difference between them, is take them as close to overlap as I can, and then I measure the distance that particle one is, how far apart the two positions of particle one are, of particle two and particle three. So I square that distance and I multiply it by the mass. And I take any trial position and then I move it around until I've minimized the sum of all those three contributions. And then I've got them in their best matched position.
Right.
And then I can make that difference ever smaller and smaller. But in that way, I can define dynamics purely in terms of relative quantities by this best matching procedure.
Right.
And when you do that, and you use the famous principle of least action, because then that's been in dynamics for 200 years and more, the principle of least action. When you do that, you find that you do recover solutions of Newton's theory for an arbitrary number of particles, but the really key difference is that the angular momentum is exactly zero. So this is a huge restriction for the whole universe. It's a huge restriction. And in addition, if there's no time, then you really have to say the energy must be exactly zero. So you get this very, very strong restriction on the solutions. And that is the way that Mach's principle is implemented for point particles interacting in Newtonian theory. So that was basically the result that Bertotti and I published in 1982. And amazingly, when you go and look at general relativity, if it's spatially closed, you can do a wonderful, there's a wonderful more sophisticated form of best matching, but it's directly, you're led directly to it. And what is very interesting in that too, if I may, while we're on it, is that you find that you don't get relativity of simultaneity. You find that there's a notion of simultaneity. So space-time normally, the normal four-dimensional space-time, you can imagine it like a loaf of bread where you can slice it in different ways. And those are different notions of simultaneity. So what you find when you do best matching to have evolving geometry is that you actually recover Einstein's space-time, but you're forced to slice the space-time that you construct is sliced in a very special way, which is called constant mean curvature slicing. And it's exactly analogous to soap bubbles in three-dimensional space. So there's something very special. So this is very, very interesting that you recover general relativity in a completely different way from the way Einstein did it. And first of all, you get general relativity without any matter. You get what's called vacuum general relativity, and all sorts of surprising things come out of it, which is perhaps too much to go into in this discussion. But I would say that the Machian idea is very vindicated as long as the universe is spatially closed, that it's a true sort of holistic unity. And sorry, do you want to come in?
Well, I was just going to ask, you know, we don't really know whether the universe is spatially closed or whether it's open. And one wonders if there ought not to be something which would be able to tell us theoretically that that was the case one way or another.
Well,
or is it purely observational?
One would hope that observations could determine it. I mean, if these Machian ideas are right, then I would say that the universe has got to be spatially closed. The observations say it's close to being flat, but the observations can't rule out that it's spatially closed, that it's larger than the current Hubble radius, but it could be, the observations are consistent with it being spatially closed.
This brings us really to the testability of the ideas which you're putting forward. Because if it's Machian, then it would need to be spatially closed. Are there any other predictions which maybe the theory might make, or is it testable in the Popperian sense of putting forward an idea and for checking?
I hope so. Now, this is perhaps where we can come on to what happens when it's not that Janus Point situation.
Yes, tell us about that, and because that might have an impact, mightn't it?
Because this is really extraordinarily interesting in my view. So there was an absolutely amazing paper published in 1918 by the Frenchman Jean Chazé, where he showed that in the problem of the n-body problem, n Newtonian particles, solutions do exist in which, lo and behold, all the particles come together and collide at an instant at their common center of mass. They all collide together. So, and that's called a total collision. Now, if you run time the other way, it becomes a total explosion. It's actually a Newtonian Big Bang, discovered theoretically 11 years before Hubble discovered the expansion of the universe. And instead of having the Janus Point situation with two half solutions, you just have the half now, which starts not with a finite size, but with 0 size in the Newtonian description.
Well, why does it only produce a one-sided? I can't quite grasp the connection between the point.
It's because actually the Newtonian equations of motion become indeterminate. There's no unique way to continue the solution after. When you come in and it hasn't yet happened, the total collision, the particles come in a very special way. They collide all together at the center of mass. And then there's no way to continue it after that has happened. The equations just fail.
Right. Okay.
Yeah. And so that's been a standard result in that theorists have come to and have concluded. So you get this situation that the universe starts, and then it looks very much like this Janus Point situation that I described, where they come out looking very uniform, and I'll come to that because it's extraordinarily uniform. But let me just say that after they've had this big explosion, they cluster and they become, the complexity increases. So you get the same effect, that this quantity that measures the complexity of the universe increases. So it looks very like what it did either side of the Janus point when the size doesn't go to 0. But what is really interesting is that the shape of the universe is very restricted at a total collision. It's what is called a central configuration. It's one in which, if you have the particles in a central configuration, the force that acts on each particle that all the other particles exert on each single particle is directed exactly towards the common center of mass, and with a particular strength, such that if you could hold all the particles in this central collision, central configuration position, and then let them go, they would fall under their mutual gravity without changing the shape until they all collide at the central collision. So that special shape, which is called a central configuration, and has been known about it, that it exists was known before Chaz's paper. That shape is determined just by the mass ratios, and it's very special. And it has a certain value of this complexity quantity, which measures how clustered they are. And what is especially interesting is there's lots of these central configurations, but there's always one for which the complexity is smallest or the uniformity is greatest. So there is just one situation. If the universe Big Bang starts in this most uniform state, it starts with the universe being in its most uniform configuration that it, or shape that it can possibly have. And then it gets a bit more clustered. So this really started giving me ideas, because we know that the universe started very uniform, or very soon after the Big Bang, it was very uniform. And currently, that is explained by cosmologists by the theory called inflation, because people were very worried that the universe would have started off in a very disorganized way. The argument for that is that it had long been recognized, particularly Roger Penrose pointed this out, that if the universe would recollapse, you would have black holes forming, and it would all be terribly messy and very disorganized, a big crunch. In contrast, it was seen that the Big Bang was extremely uniform, at least very soon after the Big Bang, it was very uniform. But then Penrose and others kept saying, well, surely by running things backwards, we should expect the Big Bang to look just like a big crunch would. Why would one end be so totally different from the other? So really, one of the big triumphs claimed for inflation is that it gets rid of that problem of the very disorganized, messy start to the universe, and with a huge period of expansion, which suddenly makes it uniform, whatever it was like at the start. And also they have a process which they actually call reheating, which ensures that the temperature is virtually the same in every direction you look. So inflation seems to solve quite a lot of problems, but it doesn't solve them all, because you have to fit certain initial conditions. They don't have any theory of how it starts, how inflation, there's no proper theory of how inflation starts. It's all right once they've got it to start, but then there are various issues with how it ends, and it's a triumph, but it's only a partial triumph. Now, it could be perhaps this idea that comes from the idea of reversing a total collision and a Newtonian Big Bang. Could it be that actually in general relativity, they'd got it all wrong, and that actually the general relativity properly treated would show that the universe does begin in a very uniform way, just as it does out of a Newtonian Big Bang? And that's what I'm working on at the moment. And I think it could be, because if so, then the theory should be testable, because the way in which it would initially become a little bit non-uniform and could be tested in the cosmic microwave background should be possible.
Right.
So I'm a bit hopeful.
Good. I'm pleased about that. Just to start to wrap up now and conclude, can I ask you a more wide-ranging question, which comes out of your book, actually? But the last chapter is quite an interesting chapter. It's about what does it all mean? And I suppose the question which struck me quite forcefully in that was, is the world a work of art?
Well, that, of course, is the question that Frank Wilczek asks. Have you read his book, A Beautiful Question?
No, I think I've got it, but I don't think I've read it.
Oh, I'm a great admirer of Frank's books. I've read 3 of them. And that is more or less what he asks right at the start, but he doesn't commit himself to it in the book, really. If these ideas that I'm trying to develop now are correct, I think it really does raise real questions about what's going on in what the universe is about, what's going on. One of the things that definitely led me to these ideas is when I read Leibniz's monadology. Leibniz says that we live in the most perfect of all possible worlds. At least that's what he told princesses. However, when you read his monadology, what he says, we live in the most varied of all possible worlds, subject to the simplest possible rules. And when I read that, it made a huge impact on me, because Leibniz is already, when you read Leibniz's philosophy, it's quite clear you couldn't possibly do any science if there were not variety all around us. How could we do it? There's nothing to work on. You've got to have something to get your teeth into or your hands onto. And so that made a huge impression on me. And then a few years ago, I met the man he just retired as the editor of Leibniz's collected works, which is a huge project. And I told him about my enthusiasm for Leibniz's idea that we live in the most varied of all possible universes. And my recollection is, he said to me, Leibniz had a second possibility, was that the universe was not always in the most varied state, but that it was trying to become most varied. And this is actually now exactly the picture that I'm developing. If the universe starts with the most uniform and least varied state it can have, and then forever after gets more varied, That's pretty interesting.
It is. And that brings me probably to my last question, which is, if we have a universe where you have increasing complexity limitlessly, I suppose, what is the end of that road? And what do we include in those complexities? Would you include such things as the complexity of life itself, of human consciousness? Is this all part of the increasing complexity that goes on? In which case, where does that ultimately lead? I mean, it's quite opposite from entropy, which leads to, you know, the total disorder and the death of the universe. This is much more hopeful in this respect.
It is, if it's right, I think it is. And I mean, I think the answer is we don't know at this stage, but I think it could completely change the way we think about the universe. I mean, it's now standard that one says that scientists don't ask questions why, but only how. If it really is the case that in this quantum form that I'm now trying to develop, I'm trying now to develop what I call quantum shape dynamics, which is based on this idea that the universe starts in absolutely the most uniform state it possibly can and then gets ever greater. This suggests, I mean, it's beginning to suggest that sort of meaning resides within the universe, that it tells its own story and that there is meaning within it. I don't know where this really leads in the long run. I mean, if this is right, this is the start of a very long journey.
Well, yes, indeed.
But certainly, I mean, there's no question that the universe is absolutely an incredible place. I mean, I'm a huge lover of sort of classical music, Shakespeare and all that. I don't see why it shouldn't be, frankly. So maybe these are big issues. I mean, the discovery of entropy and Kelvin's paper on the dissipation of mechanical energy, that sort of cast a pall which has never gone away. But maybe maybe this will reverse that process. I don't know. I mean, I don't want to make exaggerated claims.
Well, I have to say that there's a lot of science and a lot of deep thinking in your book, but there's also a lot of art as well, or a lot of literature. I was impressed by the fact that I think there were 12 or more quotations of Shakespeare in the book, and many other literary allusions, maybe crossing that gap or that divide that C.P. Snow once pointed out to us back in the 50s about the divide between science and art, and yet here you're marrying the two together. Professor Barbour, thank you very much indeed for your time today, and also for writing this book, The Janus Point, A New Theory of Time. Which,
well, thank you. I think it's a pleasure to talk to you.
Thank you very much indeed.
Okay, all right.
Bye.
Bye for now.
Bye.